most interesting one I built was a satellite called Chandra. When I worked on it, it was called AXAF. And it looks up at the sky and it collects X-rays and it takes a picture of X-rays. Now the interesting thing about that, you probably all had X-rays. Well, maybe not. If you've broken a bone or if you've hurt yourself, sometimes they'll X-ray you. The X-rays that you get by the doctor, those aren't really pictures. They're X-ray shadows. So for example, if I were going to X-ray my hand, the X-ray machine would be here, the X-ray collector or plate would be here. They'd shine the X-rays at my hand and there'd be a shadow there. But it's really a shadow of my hand. What we had to do was actually take images, like photographic images. Now, how do you think you focus X-rays? That was the first challenge, because X-rays go through everything. They go through glass. They don't go through lead, but they go through most things, or they stop in things. So we had to figure out a way to focus the X-rays the way the lens focuses light. And that was a big challenge. The other satellites I worked on were weather satellites, so they look at the Earth and they track storms. And the other satellites I worked on were called Earth Resource Satellites. They look at the Earth and they track vegetation. They can see whether plants are healthy or sick, depending on the colors they give off. And that's it.
Isn't that amazing? So,
and the reason I'm talking to you is my wife actually went to LMU and got a degree in theology, but she's a working lawyer, so a lot of times I have to sit in the classes for her. So I also have sort of a secondary theology education, which is my free.
For free.
free theology. So today, Gary, we're so glad you're here. Hopefully, we're gonna see how we can have some summer classes here, and you can run it by us. Yes.
What Sam told me you're interested in, and I'm happy to talk about, one is miracles. So I'm going to ask you, since you've all taken the class, I know that for Catholics there are 5 criteria for miracles. I can only remember 2 or 3 of them, so maybe you can help me with the other ones. So we're going to talk about miracles, and then we're also going to talk about, I think you heard a video on this, bilocation. And bilocation in the Catholic sense, what the priest was talking about, is different than bilocation in the physics sense. So we're going to talk about both of those things and see if they're actually maybe the same thing, maybe not. We'll see.
Okay, go ahead.
All right, so I'm just gonna really quickly go over the Catholic definition of bilocation. There's 5 criteria, but it can really be boiled down to something that is beyond the order of natural things, something that could be attributed really to God's doing. So, I think the best place to start with examples. So, the act of creating the world, in the Bible how God created the world, would that be considered a miracle or not? According to the definition, it wouldn't, because it's something that He willed, something that He created as part of the natural order of things, something that that wasn't considered supernatural and didn't break the current state of things. Something that would be considered a miracle is, as we saw in the Bible, like turning water into wine. Because naturally, remember how Jesus was kind of hesitant about actually committing this miracle. That could be that's a reason why He doesn't do it. It's not natural for water to become wine, or it's not natural for a few crumbs of bread to be able to feed so many people. That's why they would be considered miracles. Something that would help substantiate why God's power, but something that also breaks the natural order, something that wouldn't normally happen. So I know there's 5 definitions. I can really quickly go over them. The first aspect is something that's attributed only to God. So that was the first definition, and it's the hardest one to prove, because when it's hard to prove that something in science, it's really hard to prove that there's one cause of something, because there's so many confounding variables, so many other factors that could affect it. Like, in daily lives, we can't even tell if one thing led to the other thing. It could be a whole slew of other reasons. So that's probably the hardest problem we're coping with, trying to attribute that to God and determining whether it's really a miracle or not. And the other aspects are really relating to this idea of it breaking the natural order of things, it being supernatural. And I probably don't have to go over all the specific roles, because that's basically the idea of it.
We very seldom and perhaps never wonder, how did all this happen? We're trying to observe it and come up with rules. How does it work? How can we predict what's going to happen in the future? And what can we do with what we see? So one of the criteria for a miracle is that it be not natural, it be supernatural or extra natural. Is sort of hard for us because we see everything as natural. All we can do is observe what is, what exists. So you'll hear this in quantum mechanics when we start talking about that. To me, as a scientist, I'm putting on my scientist hat now, not my Catholic hat. A miracle is a low probability event that actually happens. Mm-hmm. So some things are very, very low probability, and we can calculate it out. For example, what's the probability that there's life somewhere else in the universe other than on Earth? There's an equation that calculates that. And that equation predicts that given the size of the universe that we know about, there are probably 10,000 other Earths or civilizations like ours that have people like us. That's a probability equation. One of the other Catholic criteria, so now I'm jumping back in, putting on my Catholic hat, is that it be observable, or they actually say sensible, which means you have to sense it. Now, the equation says there are 10,000 civilizations. Have we sensed them? No. Have we listened for them? Yes, and we don't hear them. Have we gone to Mars and looked for other life? Yes, and we couldn't find them. So far we haven't met that sensible criteria. So the criteria that a scientist uses, which are mathematics and probability and observing the natural world, don't quite coincide with the criteria that you have to learn as a Catholic what constitutes a miracle. So for me, a low probability event that happens is a miracle. But there's one other thing. For example, suppose I get cancer. That's a low probability event. Most people don't get cancer. Do I consider that a miracle and go, wow, it's a miracle, I got cancer? No. So if you want to talk about the probability idea of miracles, you have to say it has to be a desirable low probability event. So I got cancer and I shout, whoa, miracle, that's really wonderful. And now I go to the hospital and they tell me, his sister said, you're going to die. And I think, oh, that's really a bummer. I really don't want to die. I'm just going to sit here and pray. And now, all of a sudden, my body fights the cancer and I'm cancer-free. Whoa, miracle. Is that a miracle? Yeah, because it's a low probability event. I had a lot of people telling me, in all likelihood, you're not going to be here. And now I'm here. Now, that most people would say that's a miracle because it's a desirable outcome. Why did that happen? I don't know. Yes?
Mathematically, how low of a probability would it be to be considered a miracle?
That's up to you. Because, for example, if you go to Vegas and you're betting your money in Vegas and you bet roulette, and that's a very low probability event, and you win, you might say, a miracle, wow, that's great. But a lot of times it has to be a very, very low probability. We can calculate, for example, probabilities in terms of likelihood of occurrence or how long would it take to occur. For example, there is a finite probability from physics that I'm standing here and I will spontaneously disappear here and show up in Europe. That's a finite probability. But that probability is so low, I've actually read this, I didn't calculate myself, that it would take longer than the lifetime of the universe, which is about 14 billion years, for that to occur. So that would be a very, very low probability event. And that would it would absolutely be a miracle if I disappeared from here and showed up in Europe. Any questions? That was a good question. Yes.
I just wanted to pitch in a little bit about the probability.
Oh.
Most low probability occurrences are the percentage probability chance is about 10 to the negative 66% chance
Okay.
for very low probability things to occur. So for something like that, for you to just appear somewhere else, it's that percent, 10 to the negative 66-ish.
Probably.
Yeah.
And guess what? That would be, and what we do is, for example, if you flip a coin, the probability that you're talking about is you can do it in two ways. How many times does something have to happen? And then how long would it take for that many times to happen? That's sort of how we calculate probability. Any other questions?
Can you explain quantum science? Quantum science, can you explain it a little bit? In a nutshell, that kindergartner can understand.
Let's see. So just quantum.
I watched a video, a movie, and they were explaining human has made the water. So, and the outside environment has also created a lot of things with water. So the inferences by the two of the objects can be possible to explain bilocation.
Okay. So are we talking about quantum bilocation or real world bilocation?
Both.
Okay. Well, they cross over in the sense, and I think, are most of you, do you have some background in physics? So, do you know about waves? Water waves. Here's a wave. Okay. Where is that wave? Where is it? Anybody? Where is it?
Finally.
Okay. Well, is this where the wave is? So that's in one place. Is that where you would call a wave? Come on. Somebody says yes, somebody says no. Okay. Well, or is the wave here? Some of the wave's there. Most of the wave is there. Actually, not even most of the wave. That's only the peak of the wave. Most of the wave is here. So the wave is here, 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 here. Is that bilocation? Well, to a physicist, yes it is. That wave is in all those places at once. The classic experiment that people do is we have a box and we cut two slits in it and we put the wave through the two slits, and then what we notice at the end of the box is that the wave from here and the wave is there, and they interfere. So one wave goes in and we end up with two waves coming out. And that's because the wave is actually in all these places at once, and some of the wave goes through there, some of the wave goes through there. What do you think would happen if instead of two slits and a water wave, I had two slits, and then here I had a machine gun shooting out bullets? What do you think would happen? Anybody? Anybody? Okay. We've actually done this. And you can, well, I wouldn't expect you to do it with a machine gun, but if you have something that shoots out something, you can do it. The bullets come and hit these two slits, and then we get a bunch of bullets there, and a bunch of bullets there, and there's no interference. So does that mean the bullets are only in one place? One bullet either goes through this slit or that slit, but doesn't go through both slits at once? You'd say yes. Now instead of a machine gun, I'm going to have, this is going to look a lot like a machine gun because I'm not a very good drawer. I have an electron gun that shoots out electrons. And it hits that. What do you think happens? You think it behaves like the bullets or like the waves?
Oh,
Actually, it behaves like the waves. If we shoot electrons through these two slits, they interfere with each other. Yes.
so double slit experiment, so it creates alternating destructive and constructive interference.
Yes. Wow. I can tell you physics.
No, I haven't. I studied this last year for a competition.
Okay. Very cool. I bet you did well in that competition.
I actually didn't.
So electrons, which we think of as bullets, little bullets that orbit a nucleus of an atom, actually behave like waves in this experiment. And then what we found out is that even in the atom, when we try to figure out where the electron is in the atom, and people have done very careful experiments with this, we can't. So it used to be what we used to think of was the Bohr atom, where we had a nucleus, and then we had the electron. We thought of it just like the moon orbiting, and this would be orbiting a nucleus, a little particle orbiting the nucleus. But after we looked at it more carefully, what we found out is really there isn't a little particle orbiting the nucleus. There's sort of a amorphous cloud around here. And the funny thing about that amorphous cloud is we don't know where it is until we look at it. And then all of a sudden, this amorphous cloud says, oh, I'm all here. And that cloud is called the wave function, which is how quantum mechanics people describe the inside of the atom. And the fact that when we look, all of a sudden, what was everywhere now shows up in only one place, that's called the collapse of the wave function. So it's very spooky because until we look, we don't know what's going on. How many of you know about Schrodinger's cat? Okay. This actually didn't happen. No cats were damaged or killed. But Schrodinger said, let's put a cat in a box. And in the box is some poison gas. And also in the box is a little trigger for the poison gas based on the decay of a nucleus. So this is a thought experiment. We have a cat in a box. I promise. And when the experiment happens, so you're outside the box, is the cat dead or alive? When the trigger happens, the poison gas is going to be released and the cat's going to be dead. The probability that the trigger happened depends on the decay of the radioactive particle that's in there. Is the cat, when you look at it, is the cat dead or alive? You haven't opened the box. Is the cat dead or alive? Anybody? No. Both, yes. It's both dead and alive. You don't know. Now you open the box and fortunately the cat walks out. Now what happened? That superposition of dead and alive collapsed into one. Maybe sometimes you open the box and the cat's dead. Sometimes you open it and it's alive. Before you open the box, you don't know which is which. So we have to, in quantum mechanics, remember this is just a way of describing the world. In quantum mechanics, we have to say the cat is both dead and alive at the same time. That seems pretty weird to most people. It seems weird to me too. And that's the way the subatomic world works. Now, you can argue, well look, even though you didn't look in the box, the cat is either dead or alive, right? Because either the poison gas got released or it didn't. Well, how do you know? So there's a crossover between our knowledge of what's going on and what's really going on. And that's the spooky part of quantum mechanics. And maybe that crosses over into some of the miracles or the bilocation that happens. Maybe that happens Well, no, there's another bilocation. The simplest one is the wave. Wave, in a way, proves the existence of a wave. I'll go back to my water wave. The wave is moving in this direction, but the wave, the fact that we call this a wave, and if you said, where is the wave, people would point, and usually they mean, where is the peak of the wave? But that wave is actually in many, many places at once, just like the electron is in many, many places at once. And until you actually look and measure, you don't know where it is. So, is that bilocation? Yeah, to a scientist, that's bilocation. We don't distinguish between particles and waves anymore. We, in the subatomic world, call it a wave function, which is simply the probability that the wave is here, 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 here. So in a probabilistic sense, since this is where the peak of the wave is, that would have the highest probability of being called the location of the wave. But we could also call any of these places the location of the wave with lower probability. All right. And the other thing Sam wanted me to talk about is quantum entanglement. And that's another thing where things can be in two places at once. So typically what happens is we take two particles and we quantumly entangle them, and then we move them apart, and then we measure one of the particles, and guess what? Now we know what's going on with the other particle. How did that happen? That's pretty weird, isn't it? But until we measure one of the particles, we don't know what's happening in either one. But it sort of seems like measuring one particle. This typically happens in particles with something called spin. So if you spin something, it has an angular momentum, and if it's spinning in one direction, we use something called the right-hand rule, and we say the angular momentum is pointing in that direction. So there's like spin up, and then if it's spinning in the other direction, there's spin down. So we can measure spin. And we entangle these two particles. We don't know what their spin is. We pull them apart, and then we measure the spin of one, and now we can determine the spin of the other. So we measure this one as spin up, and then we know that this one is spin down. And then we measure this one, and we find out, yeah, we were right. This is spin down. How does that happen? Does one particle talk to the other one? This happens instantaneously. We know that we can communicate at the speed of light. You know that because you can talk on the phone and your friend hears you, but doesn't hear you right away. There's a slight delay. We can communicate at the speed of light. This measurement happens instantaneously. How do you think that might come about? And is that bilocation? Because it seems like the particle, the spin particle, is in two places at once. It's both here and here, because I can measure this one, and then I know exactly what's happening over here. They're connected instantaneously, not talking to each other at the speed of light. They're connected instantaneously. Why do you think that happens? And is that a miracle? To me, it's sort of miraculous, but it's not the Catholic definition of miracle. Well, the reason it happens is because things obey the laws of physics. And let me take a blob. So that's a blob with mass m. And then let me split that blob into two blobs and move them apart. So I'm going to put a little explosive charge in this thing, and it's going to be a very precise explosive charge. It's going to blow it up into two exactly equal pieces. This is side one, this is side two, and then they're going to drift apart. Now, if I look at the momentum, and physicists call momentum P for some reason, just pick the letter P for momentum. If I look at the momentum, I don't know anything about these particles. If I look at the momentum of this particle, even if the particles are far apart, if I look at the momentum of that particle, I know the momentum of that one. because there's a rule in physics, and guess what? That rule was created by God. That's how the universe works. That momentum is conserved. So the fact that I split these two up means if I measure the momentum of this, I instantly know the momentum of that, even though they're at a distance. Similarly, if I have two entangled quantum particles, and remember I said spin, so that one spin up, spin down, that one spin up, spin down, and I separate them, and here I measure the spin of that particle, and there I measure the spin of that particle. As soon as I measure the spin of this particle, I know the spin of that particle, because spin is conserved. So if there's spin up, spin down, it's a neutral particle. I blow it apart. Here, I don't know what's going on. Spin up, spin down, spin down, spin up. I don't know what's going on there until I measure it. Once I measure it, because of conservation of spin, which is another law or rule of the universe, I instantly know what's happening over there. And does that mean that this particle talked to that particle? No. What it means is that I took advantage of conservation laws and the collapse of the wave function. Because remember, the wave function is just a big cloud until I measure something and then it collapses into something definite. Yes?
Is it feasible to create a bomb using antimatter?
Is it feasible? Well, so far we've only been able to create antimatter in a laboratory and very little, because guess why? Because there's too much matter. So if we create antimatter, it almost instantly disintegrates. So you can't create a lot of antimatter. So the short answer to your question is no, because we can't make enough antimatter. But the real trick is, why isn't there more antimatter? Let's assume in the beginning that because antimatter is just a different kind of matter, in the beginning there was equal amounts of matter and antimatter. What do you think would happen in that universe? Nothing. Because the antimatter and matter would interact with each other and create energy. That universe would just be full of energy, there would be no matter left. So for some reason that we don't quite understand, we believe that in the beginning of our universe, there was slightly more matter than antimatter, and most of the antimatter ate up most of the matter and created probably this stuff we call dark energy and dark matter. And what's left is the matter, and that's, we're living on the matter that's left over from that. Yes?
One of the laws of physics or thermodynamics, I don't remember which, but it said that matter cannot be destroyed, but doesn't antimatter destroy matter?
No. The complete law is matter and energy cannot be created or destroyed. Only God can create matter and energy. We and the universe can't create matter and energy, but it can be changed in form. So, for example, when an atomic bomb goes off, there is a bright flash, a lot of energy, a lot of heat. And guess what? If you could collect all the stuff from that bomb and measure its weight, it would weigh slightly less. Some of the matter has been converted into energy. And how many of you have played with firecrackers? Don't raise your hand because I don't want to get you in trouble. But when the firecracker goes out, that chemical reaction that creates light and heat and sound, that's energy. Some of the matter from that firecracker disappeared and became energy. Now, could we collect all of that and measure it and say how much matter disappeared? The answer is yes, but it would require such a sensitive scale that we probably would never be able to build such a scale to measure all the pieces and the smoke and all that. We'd have to collect everything and figure out just how much matter got created, or how much energy got created and how much matter got lost. Yes?
That's Disneyland, right? The
Yeah.
firework.
It is. Well, when you heat something up on the stove, you're using up some matter. When you heat anything, when you strike a match, you're using up some matter, but it's becoming energy. And then what happens in the universe is there are places where new stars are created from leftover gas and energy, and so the universe is sort of replenishing itself. So don't worry, we're not going to run out of matter. Yes.
If we create like really heavy antimatter, like stuff that doesn't naturally occur, then what would that do?
I don't know.
Like, is it possible to create very heavy antimatter?
Well, the only thing we've been able to create now is very, very small pieces of antimatter, like an anti-electron or an anti-proton. So we haven't been able to actually put those together into anti-hydrogen or anti-helium. So the answer is, right now our technology is such that we can't create enough antimatter. We can only create little tiny bits of antimatter. Yes.
How are entangled particles created artificially, or like manually? How do we create artificial?
Okay, there are experiments that people do. What you have to do, first of all, is isolate the particle and create cool, very super vacuum and near absolute zero temperatures. Then you can actually create two entangled particles. And the reason I know this happens is they've done the experiment. So in this very, very cold, very, very pure environment, they create two particles, entangle them, and all that means is they take something and move it into two pieces. So the quantum mechanical wave function of this first particle gets split into two particles. We let it decay into two particles. So we have a wave function for each of those. And then you can actually move them apart in this environment. And as far as we can tell, this quantum entanglement doesn't depend on how far away you are. So we've got it close together, and we've got it far apart, and quantum entanglement still holds. So it looks like there's something happening at a great distance. It's one of the spooky parts of Does that answer your question? So it has to be very cold,
Yeah.
and very, very vacuumy.
Also, because let's say you bring them a far apart distance, these two particles, right? Isn't information being transmitted across a vast distance faster than light in a sense? So that's it kind of breaks.
That's an excellent question. And the answer is, it looks like it's being transmitted faster than the speed of light. But really, all that's happened is I've taken an unknown, the wave function, remember, is a probability. I've taken an unknown here, and now it becomes a known. And because now I know that, and because they were quantumly entangled, nothing has been transmitted. Only my ignorance has been relieved. And I'll give you another experiment. How many of you have a laser pointer? And you don't have to raise your hand if that's uncomfortable. But take a laser pointer,
Everybody
and it'd have to be a pretty good laser pointer, and point it up at the moon, and then flick your wrist like a degree. And what will happen is that it'll look like the dot on the moon went from the bottom of the moon to the top of the moon in a fraction of a second. Now you have to take into account the speed of light, so you have to do this over and over again. But in a way, it looks like you've just gone faster than the speed of light, because how can I get from the top of the moon to the bottom of the moon, or the bottom of the moon to the top of the moon, or the left of the moon to the right of the moon, so quickly? It would take, that dot is moving faster than the speed of light. Oh, no, it isn't. Light's still moving. It's an illusion. It's like a magic trick. It looks like the thing is moving faster than the speed of light because of the way our eyes perceive motion.
So you describe miracle and what, and magic at the same time, huh?
Well, in a way, magic is taking advantage of miracles and realize magicians aren't really doing anything miraculous. They know how people perceive things and how people think, and they're sort of tricking them. There are true miracles in the Bible, and as you heard in the video. But that's why it takes a careful investigation to make sure what's really a miracle and what's just a magic trick. So suppose I say my priest is, I met him here, and then my friend who's in San Diego says, oh yeah, I saw your priest yesterday in San Diego. I said, well, that's impossible because he just gave the homily here. How could he be in San Diego too? Well, one possibility, since my priest is really not a miraculous priest, like you read about, is that there was somebody who looked exactly, sounded exactly, or similar enough to my priest. So it looked to this person like, oh, your priest is in San Diego. And plus that person doesn't know my priest as well as I do. So maybe if I had been there observing this person, I would have said, yeah, he looks a lot like Father John, but no, that's not really Father John, because Father John has this slight limp when he walks, and this guy had no limp when he walked. So you have to, that's why miracles have to be investigated very carefully, because a lot of times people would like to believe that something is miraculous and really can be explained as a magic trick, a rule of physics, or just a mistake. Yes?
Yeah, so this is kind of like a phenomenon, right? Like you explain in the sense of quantum science how this works. So how does that apply to, like in the case of Father Q, right? Like it's a human being where, it's
It does not. That's why that's a miracle. And this, while it seems miraculous, I wouldn't say is a miracle. And given what I said earlier, that all physicists and really scientists do is observe the natural world, describe it, and try to figure out why does this happen and when will it happen, so I can predict something in the future. Nothing we do is miraculous, because it's all about nature and what really exists in nature. And it appears miraculous when we do wonderful things like, oh gee, wow, I just separated these two things, and I measured this one, and instantly, because I had my buddy over here in Chicago, look at his piece that I moved over to Chicago, instantly, I knew what he was going to measure, and he measured his thing. That seems like a miracle, it's not. It's a law of nature.
So would you say that science and faith has a little gap?
Yes.
That perhaps science is a continual learning?
Well, for me, one beautiful thing about science is it actually makes you appreciate God more. Because when you think about it, most of the world, most of the universe is pretty miraculous. It's pretty miraculous that I'm up here talking. How many other animals do you know talk? And it's pretty miraculous that my body works. Sometimes I get sick, and then my body heals itself. That's pretty miraculous. Miraculous in the sense that there's no real reason for that. It's not miraculous in the sense that if I get a cold and then I get better, I don't say, miracle, wow, I got sick and then I'm better. But if I get cancer and I get better, I might think of that as a miracle. Now, the question is, what's the cause of that miracle? What's the origin of that miracle? Is it a Catholic miracle? Probably not, because really what it was is my body getting its repair mechanisms revved up and fighting the cancer, fighting the disease, and then I got better. And there are stories in the Bible of blind people being able to see. You'd actually have to think about that. There are blind people now who have been blind since birth, and then they can see eventually. Is that a miracle? Well, you have to look at what happened. How much damage was in their eye? how did they get better? How did they heal themselves? If there was so much damage that there was no possibility of healing, then you would call it a miracle. But if the body simply heals itself, is that a miracle? I sort of think it's a kind of miracle, but not a Catholic miracle.
It's a miracle, but that it's not what canonical, right? The church didn't approve it.
Right, as
In
Sam
fact,
said,
there's more miracles than we know of.
well, as Sam said, the first criteria is it has to be, and this sounds weird, unnatural. In other words, you can't explain it by nature. So if you invoke the laws of physics, like this I think, to me, is pretty miraculous that happens, but it's consistent with the laws of physics, so that's not a Catholic miracle. If I get sick and I get better, that's not a Catholic miracle. Even if the doctors say I'm going to die, and I get better because my body healed itself, is that a Catholic miracle? I don't know. Again, you have to look at the unnaturalness of whatever is going to occur.
For some people they were sick before, so is that a miracle?
Yes.
Wait, what would be like the opposite of a miracle? Like something that has low probability but has a non-desirable outcome?
Oh no, I consider that a miracle. Like I said in the beginning, if I got cancer, I'd consider that a miracle. I wouldn't celebrate it, but there's a very low probability that I'll get cancer. Now, what I celebrate as a miracle is when I heal myself from the cancer, or when nature heals me, or my body heals me.
Or have you actually had cancer?
Well, actually, good question. I had this experience. I had a minor operation, an operation that's been done tens of thousands of times. And I had that operation, and as a consequence of something they gave me during the surgery, my liver failed. And they put me on a liver transplant list. So I was going to die, probably, because you very rarely get a new liver. And then, when I was sitting in the hospital, all of a sudden, the numbers turned around, and my liver healed itself, and now I'm okay, obviously, I'm talking to you. Was that a miracle? Well, I thought it was sort of a miracle. I didn't think it was a miracle when my liver failed, but when I look at my physics definition of miracle, a low probability event occurred. My liver got killed by some innocuous substance that they gave me during surgery, and my liver repaired itself. That I do consider a miracle. Both of those were low probability events that happened. So the answer is, you have to think about miracles in a different way.
That was just half a year ago, huh?
Yep, that was, it was actually on Valentine's Day of last year. I remember it because it was Valentine's Day, and my wife was pretty upset we didn't get to celebrate Valentine's Day. I was dying.
Question. Yes. Have you heard of some kind of scientific theory saying that everything occurs at the same time and just happens? We see only this particular incident.
Yes.
For example,
Okay, what he's alluding to is there's actually a theory, and remember this is a theory because, the two major things I know about Catholic miracles, or Catholic verification of miracles, one is it has to be unnatural. Number two is it has to be sensible, which means you have to observe it with your senses. So when I'm talking about theories, realize some of those, this used to be a theory, but since people have figured out how to do the experiment, it is now sensible. But the idea that everything happens at the same time, all at once, that's a theory called the multiverse theory. And this will perhaps shock you. If this theory is correct and there are multiverses, not only is everything happening at the same time in different locations, and this requires, by the way, an infinite universe. Universe, I'm now putting in quotes because Now I don't mean the observable universe that physicists talk about. I mean the universe meaning everything that exists. If we're in a multiverse, which is our universe without quotes is in the bigger universe, which is the multiverse, then not only is everything happening at the same time and we're only seeing one piece of it, but guess what? You've got duplicates. And there's somebody exactly like you in another universe doing different things than you do. And in fact, everything you might have done is happening somewhere. And so some of you have flunked out of school, some of you already have your PhDs, some of you get married, some of you don't. So everything happens in this infinite multiverse, and it all happens sort of at the same time.
Then go back to my questions or comment. Okay. Based on that ideas, is it something go wrong or something just cut in, appearing for the Pedipier's case, it appeared in 2 locations, and because according to that theories, it happens.
Yep.
But just something go wrong or something we don't know, and that cut in, and then that father appeared in both cases.
Okay, that's sort of, he said cut in, but I'd say he's talking about when worlds collide. So suppose there are 2 of me, because remember I just told you in the multiverse there is another one of me. In fact, there's a bunch of other ones of me. If, for example, I don't know if you know about a Venn diagram, but here's everything over in our universe, here's everything over in the other universe, and then for some reason, some unknown reason, those 2 universes overlap or collide, then things that are happening here are also happening here. So I actually could be in, that's me in the one multiverse and me in the other. I could be in 2 places at once. And so that is one possible explanation for bilocation. And that would be, remember this is a theory, and physicists say we observe nature, but we have theories about all sorts of things. We've never seen that. So that actually would be a miracle, because that's an unnatural thing. As far as we know from what we observe here, a multiverse is possible, but only in our brain. We haven't really seen the multiverse yet, but maybe we do when we see these miraculous bilocation events. So that's a very good question.
Yes.
Are you aware of any miracle that happened in the past that has proven not a miracle by theory of physics?
I do know that there have been some hoaxes, and I only remember things that I've seen on TV. For example, if somebody says, I have a miraculous cure because of the waters, this was actually a Monk episode, like the show Monk. And, they convinced people that the water from this particular fountain was miraculous and it would cure your diseases. And it turns out they were just tricking the people, and that proved to be a hoax. I don't know of anything that I can cite in the real world, but be careful of hoaxes that, I'll give you an example I can actually cite. A friend of mine had a girlfriend who got cancer, and she was dying. So they sent her her family sent her to Mexico for the miracle cure of Laetrile. And so she spent a lot of money getting this Laetrile, which is basically sodium cyanide extracted from peach pits, and she died. So that was preying on her hope for a miracle and tricking her into spending money and not really having a miraculous outcome. Now, if she had lived, I don't know if she would